Hello, everybody. This is Paul again. And now in this fast tutorial, we are going to learn how to create a new propulsion architecture. So in fast, we allow you to either A, use one of the shipped propulsion architectures, and there are 6 of them. Make sure to check out the README in the aircraft specs package to learn which ones are shipped with fast. But now we're going to focus on creating our own propulsion architecture. So in the previous tutorial, we talked about the matrices that we use to describe the connections in the propulsion architecture. And if you haven't seen that video yet, I recommend that you watch that one first before coming to this one. I'll also recommend that you read the paper here, A Framework for Electrified Propulsion Architecture and Operation Analysis, so that you better understand the methodology behind this graph theory-inspired approach to represent power flows in a propulsion architecture. So the last tutorial gave a brief overview, but the paper will go into much more detail. So now what we're going to do is we are familiar with the matrices from the previous tutorial that represent the propulsion architecture. Now we're actually going to make a new propulsion architecture, develop the matrices that we need, and then input them into fast. So let's get started. The new propulsion architecture we're going to model is a series parallel hybrid architecture. So if you remember in the last video, we had a parallel architecture which involved the turbo shaft connected to a gearbox and fan, as well as an electric motor being connected to that same fan. We also have elements of the series architecture because we also have the turbo shaft connected to a generator connected to a motor. So we can see we have a little bit of both architectures going on here, hence the series parallel. So since this is the first time that some of you may be making these propulsion architecture matrices, what we're going to do for simplicity is actually get rid of the generator. That way we only have 2 power sources that we're looking at. And now let's see what the architecture matrices would be, and we'll walk through why they are the way they are. So as a reminder, the TSPS matrix represents the connections between the thrust sources and the power sources. We have 1 thrust source and 2 power sources, which is why it's 1/2. And both the turboshaft engine and the electric motor are connected to the fan, which is why they both have 1s. The power source matrix, again, is 2/2 because we have 2 power sources. Again, each power source drives itself, which is why we have the 1s on the diagonal. And then the turbo shaft engine is also driving the electric motor, which is why we have the 1 in the 2-1 entry. And again, always remember that columns drive rows. So the turbo shaft drives the electric motor. For the PSES matrix, that is also 2/2 because we have 2 power sources, 2 energy sources. The turbo shaft is just connected to the fuel and not the battery. Similarly, the electric motor is not connected to the fuel, but only the battery, which is why we have the 1s on the diagonal. So now what we're going to do is move on to figure out how we are going to describe the power flow between the components. So you can imagine that the turbo shaft is providing some of the power to the fan, but the motor is also going to be providing some power as well. So we need some sort of way to be able to describe how the propulsion system is going to operate. And for that, we have the operational matrices. So I've taken the liberty to color code all of the connections and split them up so it's a little bit easier to see what's going on. But you'll notice that the operational matrices are the exact same size as the architecture matrices. The only difference is now instead of putting in 1s and 0s, we are going to be putting in power splits, which are described by the variable lambda. What is lambda, or what is its definition, you may be asking? Well, the power split lambda is defined as the power from component X to component Y divided by the power required by component Y. So you can see in the example here, I have 0.8 in the first entry of the TSPS matrix. So that means that 80% of the power required by the fan is going to come from the turboshaft engine. Similarly, 20% of the power required by the fan is going to come from the electric motor. Since the power sources drive themselves, we keep the ones on the diagonal. And we're also going to say that 40% of the power required by the electric motor is going to come from the turboshaft engine. Similarly, 60% of the power required by the electric motor will come from the battery. Lastly, the turboshaft is only connected to the fuel, so the fuel is providing all of the power to the turboshaft, which is why we have a 1 here. So you can see it's pretty straightforward, but make sure to read the paper that is cited down below to gain a better understanding, because this is a very elementary introduction. So we've covered the architecture, we've covered how the power flows in the architecture. The last thing we need to cover is the losses or inefficiencies of the components along the powertrain. And for that, we have the efficiency matrices. So again, they are the same size as the architecture and operational matrices. All that the entries represent is the efficiencies of the upstream components. So for example, in the TSPS matrix, if we travel along this route or path, we encounter the gearbox and the propeller. So when we're figuring out the power required by the turboshaft engine, we have to consider the efficiencies of the gearbox and the propeller. We have to do the same thing for the electric motor. Now, when we consider the PSPS matrix, remember earlier that in the architecture matrix, there was a 0 up in the upper right corner, indicating that there is no connection from the motor to the turboshaft. In fact, it's the other way around, right? It's the turboshaft to the motor. So anywhere where we would normally have a 0 in the architecture matrix, we now put a 1, so that way we can avoid a divide by 0 error. And make sure to read the paper below for more details about that. So the upstream component that the turboshaft engine encounters is the electric motor. So that's why we have the electric motor efficiency down here in the 2-1 entry. And then going from power sources to energy sources, the upstream component for the fuel is the turboshaft engine, which is why its efficiency is here. And then from battery, we have the power converter and the electric motor upstream, which is why we have both of those efficiencies here. And again, remember, there were 0s here on the off diagonals earlier because there are no connections between the fuel and the electric motor or the battery and the turboshaft engine. But again, to avoid that divide by 0 error, we set these to be 1 for now. So as you can see, putting together one of these sets of architecture, operational, and efficiency matrices isn't that difficult once you know what's going on within your system. So now that we've done the theory or the math on paper, what we're now going to do is show you how to program this into FAST. So let's switch over to FAST. And one thing I might not have mentioned earlier, I'll mention it again, is that any MATLAB script I open or any lines in the command window that I run are always going to be provided in a little short MATLAB script called tutorial number in the tutorials package. So feel free to open up any .m file that corresponds to the tutorial you're watching, and that will have some more information either about the scripts that were opened or the lines of code that were ran. So we are in tutorial 7 now, so let's open that. And what we're going to do is begin to input all of the power splits and propulsion architecture matrices into MATLAB. As a reminder, if you forget what parameters belong where, you can always check out the README in the aircraft specs package. If you scroll down to the table with all of the parameters in it, there is a large section on all of the different power splits that you can put in. All right, so just make sure to come down here if you need. But anyway, let's go back to our MATLAB function or script for this tutorial. So what we're going to do is first, we're going to load an aircraft, and we'll just load the example aircraft that we used in the previous tutorials. And if you remember that one, for simplicity's sake, we were just modeling in ERJ 190, which has a conventional architecture. So what we're going to do is now create the propulsion architecture and put it into FAST. So the first thing I'm going to do is I'm just going to define arbitrary component efficiencies. So we have the turboshaft, the power converter, the electric motor, the gearbox, and the propeller. So we'll use these when we're defining the propulsion architecture's efficiencies down below. Now remember, in addition to inputting the matrices, we also need to change the propulsion architecture type. So if you remember earlier, I was talking about the 6 possible propulsion architectures that we ship with FAST. And then if you want to specify one yourself, you provide an O for the architecture type, which is what we did here. So now let's start making our architecture matrices. First one is the TSPS matrix, which if you remember from the slides was 1, 1. The PSPS matrix was 1, 0, 1, 1. The power sources to energy sources connections were 1, 0, 0, 1. And now we'll get into the operational matrices. One thing we didn't talk about in the slides was that what do you do if you have multiple fans running, right? You need to split up the power that each of the fans is taking. So in this example, we only had one fan, so we can just leave this split as a 1. However, if you had 2 fans, maybe the power is being split 50%, 50%, like it is on most aircraft. So instead of having a 1, you would have 0.5, 0.5 to represent that one fan is accepting 50% of the power or providing 50% of the power, and the second fan is providing the other 50%. For now, we'll leave it as 1. So next, we're going to input our TSPS, PSPS, and PSES matrices, and you'll notice that I hard-coded in the values from the slides. However, you'll notice that all of these are actually written as function handles. So what that allows us to do is change the power management strategy on a segment-by-segment function. So let's say I actually wanted to change how I'm splitting the power between the electric motor and turboshaft engine as a function of the segment. What I could do is instead of hard coding something, I could input a variable called lambda, perhaps, and change this to represent 1 minus lambda, and change this to lambda. So now the power output by the fan is still going to add to 1. We're just splitting it depending on the segment that we're flying. So that's a really nice feature of FAST. You can change the power management strategy as a function of the segment. Anyway, let's put it back to what we had it at. And now we'll move on to the efficiency matrices. So again, for the thrust source power source connections, we run into the gearbox and propeller. So we multiply them together for both sources. In the PSPS matrix, again, the turbo shaft engine is driving the electric motor. So we consider that efficiency here. And then for the power sources to energy sources, the only thing upstream of the fuel is the turboshaft engine, but upstream of the battery, we have the power converter and the electric motor. Now you'll notice one more thing, in addition to all of the matrices that you input, you have to tell us the energy source type and power source types that you're using. And that way FAST uses the appropriate models for each. So again, for the energy source type, put a 1 if the energy source represents fuel, and a 0 if it represents a battery. And then for the power source type, put a 1 if it represents the engine, or 0 if it represents the electric motor. Okay, so now we have everything in MATLAB. What I'm going to do is run this script, and then we'll see an aircraft structure pop up in the workspace over here, and then we'll just take a look to see where all of the information is stored. So let me make an output structure called aircraft and set that equal to the tutorials package. And we are in tutorial 7. And here we have our aircraft structure now. So what we can do is we can open that up. And again, we were changing the aircraft specifications, not the settings. So let's go into specs. We were looking at the propulsion system. So we'll open that substructure up. And here we are. So now if we look at the architecture, we can see that it is of type O or other, which means that the user is prescribing it themselves. If we look at the propulsion architecture, we have the TSPS, PSPS, and PSES matrices, just as we prescribed them, along with the energy source and power source types that we prescribed. Now, if we look at the operational matrices, we have the TS matrix, which again, we only have a single fan, so that's why it's just 1. The TSPS, PSPS, and PSES matrices are split accordingly, as we had defined it in the slides. And then, if we look at ADA for the efficiencies, we have the propeller efficiency, and then we also have some of the component efficiencies multiplied out. So the 72% represents the gearbox and propeller efficiencies being multiplied, and the 0.912 represents the combined efficiencies of the power converter and the electric motor. So as you can see, there's a bit of effort required to create one of these architectures, but the nice thing is that the user is in complete control over it, and you can come up with some really cool novel propulsion architectures. So this was a quick little insight into what you can do with these efficiency matrices, and we hope, all the propulsion architecture matrices, and we hope that this was a helpful tutorial for you. So with that, we would like to thank you for joining us. Don't forget to check out our lab website, ideas.engine.umich.edu. And this wraps up the tutorials on the propulsion architectures. So at this point, we've installed FAST, we've sized an aircraft with it, we've now spent some time looking at the aircraft specification files and the mission profile functions. Now you have the propulsion architecture matrices at your disposal, as well as coming up with new novel propulsion architectures. And in later videos, what we'll do is start talking about geometry. So now that we know how to run an aircraft, we know how to prescribe the configuration and everything about it, let's start seeing the results we get out from FAST in terms of the geometry and the propulsion architecture schematics. So thanks again for watching, and we hope to see you in a future tutorial.